A box can sit still while you push on it, then suddenly break loose and start sliding. Nothing magical happens at that instant. The friction force has changed its role. Before sliding begins, static friction adjusts to prevent motion. After sliding begins, kinetic friction acts with a more fixed magnitude. In this video, we will learn how to tell which kind of friction is acting, how to calculate it, and how friction changes the acceleration of an object on a ramp. Whenever an object is in contact with a surface, the surface can exert a contact force on that object. That contact force can be separated into components. The component perpendicular to the surface is the normal force. The component parallel to the surface is the frictional force. Friction acts along the surface, and it opposes relative motion between surfaces in contact. The phrase relative motion is important. Friction does not simply oppose motion in every situation. It opposes the sliding or the tendency of sliding between the two surfaces. For example, if a block is sliding to the right across a table, kinetic friction on the block points to the left. If a block is at rest but you try to push it to the right, static friction may point to the left to prevent the block from beginning to slide. So the first question in any friction problem is, are the surfaces sliding relative to each other, or are they not sliding yet? Static friction acts when two surfaces are not sliding across one another. The word static means that at the contact surface there is no relative sliding. Suppose you pull gently on a block resting on a horizontal surface. If the block does not move, then your applied force is being balanced by static friction. As you pull harder, static friction can increase to match your applied force, as long as the block still remains at rest. This is why static friction is different from many other forces students have seen. It is not always equal to one fixed value. It adjusts to whatever value is needed to prevent slipping up to a maximum limit. Static friction opposes impending relative motion. Impending means the motion that would happen if friction were not strong enough. So, if your pull would make the block slide to the right, static friction points to the left. When the applied force becomes large enough, static friction reaches its maximum value. After that, the block begins to move. Now let us write the mathematical conditions that describe how large static friction can be. The magnitude of static friction can have any value from 0 up to a maximum value. Mathematically, we write F sub s is less than or equal to mu sub s times n. Here, F sub s is the magnitude of the static frictional force. The symbol mu sub s is the coefficient of static friction. The normal force is represented by capital N. This equation is an inequality, not always an equality. That is extremely important. This equation is an inequality, not always an equality. That is extremely important. Static friction does not automatically equal to mu sub s times n. Instead, mu sub s times n gives the maximum possible static friction. If the object only needs 5 newtons of static friction to remain at rest, static friction can be 5 newtons. If the object needs 20 newtons and the maximum static friction is 30 newtons, the object can still remain at rest. But if the object needs more than the maximum value, static friction can no longer hold it in place and the object begins to slide. Once sliding begins, we switch from static friction to kinetic friction. After the surface starts sliding, the friction force is called kinetic friction. Kinetic friction acts when the object is sliding relative to the surface. Unlike static friction, the magnitude of kinetic friction is usually modeled with an equality. We write F sub k equals mu sub k times capital N. Here, F sub k is the magnitude of the kinetic frictional force. The coefficient mu sub k is the coefficient of kinetic friction. The normal force is again represented by capital N. Kinetic friction acts opposite the direction of sliding motion. If a block slides down a ramp, kinetic friction acts up the ramp. If a block slides to the right across a floor, kinetic friction acts to the left. The coefficient of kinetic friction is usually smaller than the coefficient of static friction for the same pair of surfaces. That is why it often takes more force to start an object moving than to keep it sliding. The values of the coefficients depends on the pair of surfaces in contact. So let us look at some examples. The table lists approximate coefficients of static and kinetic friction for different pairs of materials. The coefficient depends on both surfaces, not just one object. For example, rubber on dry concrete has a much larger coefficient than steel on ice. This means rubber on dry concrete can produce a much larger frictional force for the same normal force. Notice that the static coefficient is generally larger than the kinetic coefficient. This matches the idea that it is usually harder to start sliding than to keep sliding. However, these values are approximate. Real friction depends on surface condition, temperature, roughness, contamination, and other details. In textbook problems, we use the coefficient provided in the problem or in a table like this. The coefficient itself does not have units. Since friction equals coefficient times normal force, the units of friction comes from the normal force, which is measured in newtons. Now we will apply kinetic friction to a block sliding down an inclined ramp. Consider a 10 kg block sliding down a ramp. The ramp is inclined at an angle of 30 degrees. In part A, we are asked to find the coefficient of kinetic friction between the block and the ramp if the kinetic frictional force is 45 newtons. In part B, we are asked to find the acceleration of the block. Because the block is sliding, the friction is kinetic friction, not static friction. The block slides down the ramp, so kinetic friction acts up the ramp. As usual, for incline problems, we choose our axis so that the x-axis is parallel to the ramp and the y-axis is perpendicular to the ramp. This choice makes the motion one-dimensional along the ramp. The component of weight parallel to the ramp is given by mg sine theta, and that is pointing down the ramp. The component of the weight perpendicular to the ramp is mg cosine theta, and that's pointing into the surface. The normal force acts perpendicular to the surface away from the ramp. Since the block does not accelerate perpendicular to the ramp, the normal force equals mg cosine theta. Let us now draw the free body diagram and organize the force components. The free body diagram shows three forces acting on the block. The weight acts straight downward. The normal force N acts perpendicular to the ramp away from the surface. The kinetic friction force F sub k acts up the ramp because the block is sliding down the ramp. Now we break the weight into components using axes aligned with the ramp. The x-axis is along the ramp, and we take positive x to be down the ramp in the direction of the block's motion. The y-axis is perpendicular to the ramp, and let's say the upward direction here is the positive y. Now let's organize the forces and components in a table. The x component of the weight force is given by positive mg sine theta. The y component is negative mg cosine theta, and it is negative because the y component is pointing in the negative y direction. The normal force has no x component. In the y direction, the normal force is positive n. The kinetic friction force has no y component. Since the block does not leave the surface or sink into it, the acceleration in y direction is 0. Therefore, the y equation gives n minus mg cosine theta equals 0. And that gives us n equals mg cosine theta. Now we can use the normal force to find the coefficient of kinetic friction and then calculate the acceleration down the ramp. For part A, we have to find the coefficient of kinetic friction. For that, we can use this equation. Kinetic frictional force is equals to coefficient of kinetic friction times the normal force. And we can rearrange this equation so we get coefficient of kinetic friction is equals to frictional force divided by the normal force. And then we can substitute the values we found. So we get mu sub k is equals to 45 newtons divided by mg cosine theta, and then we can substitute the values to this. So we have 10 kilograms times 9.8 meters per second square times cosine 30 degrees. And this is equals to 0.530. And that is the coefficient of kinetic friction. And for part B, we have to find what is the acceleration of the block. So the acceleration of the block can be found using Newton's second law. So F net in x direction is equals to mass times acceleration in x direction. So the net force will be mg sine theta minus fk, and that will be equals to mass times acceleration in x direction. So we have 10 kilogram times 9.8 meters per second square times sine 30 degrees minus 45 newtons equals 10 kilograms times acceleration in x direction. So we can rearrange this equation. Ax is equals to 10 kg 9.8 meters per second square sine 30 degrees minus 45 newton divided by 10 kg, and this is equals to 0.4 meters per second square. The positive result means that the acceleration is down the ramp because we choose positive x to be down the ramp.